Greetings. So, till now, we have introduced the concept of hydrodynamic boundary layer, in which we conveyed that when the undisturbed fluid having velocity u infinity enters the the domain in which a flat plate is placed, it will experience velocity gradients near the wall in very thin region, and that thin region is called the boundary layer region, where velocity gradients are predominant and effect of viscous shear is felt a lot. Okay, so moving on, we will introduce the concept of thermal boundary layer region. So before that, we must know that when the thermal boundary layer will form, the thermal boundary layer, as the name suggests, analogous to velocity boundary layer. In velocity boundary layer, velocity gradients are present. In thermal boundary layer, temperature gradients are present. So temperature gradients will be present when the surface temperature of the plate and the fluid temperature are significantly different. If they are both at same temperature, then the no thermal boundary layer will form at all. So this is the necessary condition for formation of thermal boundary layer, that surface temperature and the fluid temperature should not be the same. When the undisturbed fluid enters the domain of the flat plate or any body, right? So let us assume that cold fluid having ambient temperature T infinity enters the domain where flat plate is placed, which is maintained as a constant temperature at every point as Ts, and suppose that Ts is greater than T infinity, which is the fluid undisturbed temperature. Because of the no slip boundary condition, the immediate layer of the fluid comes in contact and will have zero velocity on the surface of the plate, and since this layer is having zero velocity, it will receive heat from the plate by conduction, and it will immediately reach the thermal equilibrium, means the same temperature as the plate, and rest of the fluid will have the undisturbed fluid temperature. If we see here, so this is I am talking about. So when it first comes in contact with the wall, so the immediate layer will reach the surface temperature Ts, and rest of the fluid will have T infinity everywhere, right? Note that we are not providing any arrows in the fluid when we are representing the temperature, because temperature is scalar. But when we are showing the velocity distribution, we are showing the arrows because velocity is a vector, right? So when the fluid is near to the leading edge, only the fluid which is very much near to the wall will have the same temperature as that of the wall, and because of that, temperature gradients within the fluid will be very much high, and these temperature gradients will become lower and lower as the fluid will flow from the leading edge to the trailing edge, that is the back of the plate, right? Because more and more fluid become hotter and the temperature gradients will become lower and lower, right? Because more and more energy will come right as we move, so that's why the temperature gradients will become lesser and lesser. So at this point, the tangent, if we draw, which will represent the temperature gradient dt by dy at y is equal to 0, will be higher here as compared to if we draw the tangent here. And if we go further down, the temperature gradients will be even lesser, right? So temperature gradient will be higher when the tangent is closer to the wall. So that is the logic, right? So along the plate the fluid will become slower and hotter, slower because of friction and hotter because of thermal energy entered into it, right? So temperature gradient decreases along the plate. Along the plate. So this thin region where temperature gradients are significant, which I am marking like this thin region is known as thermal boundary layer region. Because here temperature gradients are significant. This temperature gradient are of very much interest to us because we will be using this thing, we will be using this parameter in finding the heat transfer coefficient, right? So if we want to find the heat flux because of the temperature gradient, we can find like minus Kf thermal conductivity of the fluid, Kf is thermal conductivity of the fluid times temperature gradient of the wall, right? So at x equal to 0, here temperature gradients are highest, temperature gradients are very much high, so heat flux will be high. But as we move along the plate, means as we go along the plate, x will increase, the temperature gradient will decrease, and as a result heat flux will also decrease. Alright, and from Newton's law of cooling we can rewrite the heat flux as heat transfer coefficient times Ts minus fluid reference temperature, and here we are using the fluid reference temperature as the undisturbed fluid temperature. Right? If we equate this equation, if we equate this equation and this equation, minus Kf dt by dy at y is equal to 0 equals to h times Ts minus T infinity. So we can find the h as minus Kf dt by dy equal to 0 divided by Ts minus T infinity. So this will give us the heat transfer coefficient. Of course, it will be the local heat transfer coefficient because h can vary with the location, right? Because Ts is constant for constant surface temperature boundary condition, but this gradient is changing at every x. Because of that, its effect will be reflected in the h also, because we can see here that the temperature gradient is different here than here, right? So as a result, heat transfer coefficient will also be changing, right? So as temperature gradient is highest at x equal to 0, so the heat transfer coefficient will also be highest at that point. So if we write this temperature gradient, approximately it will be like Ts minus T infinity divided by, at surface temperature we will be having 0, delta 0, length 0 distance, and at where T infinity is there we will be having boundary layer thickness, right? So approximately it will be like T infinity minus Ts divided by delta T. So if we equate with this Ts minus T infinity equal to minus Kf dt by dy at y equal to 0, we will get H as approximately Kf by delta T, right? So as we can see from here also that as we are moving along the length, delta is increasing. So as delta increases, boundary layer thickness increases in the plate, the heat transfer coefficient is going to decrease. And also temperature gradients are also decreasing along the length of the plate. Which will result in lesser heat flux. That's why thermal boundary layer thickness layer is treated like a insulated layer over a surface, right? So to calculate the heat flux, either we need the heat transfer coefficient or temperature gradient at the wall, right? Moving on, I would like to introduce some non-dimensional numbers which are of great interest for the convection heat transfer. The one is Prandtl number. It defines the ability of the fluid medium for momentum diffusion with respect to the ability of the medium for thermal diffusion. It also means, in general sense, it means that up to how much distance the friction can enter and up to how much distance the thermal energy can enter within the fluid medium. So these two competitive things means which will be winning, means thermal diffusion and momentum diffusion, who will be winning, that will depend on the Prandtl number. So it is defined as momentum diffusivity to thermal diffusivity, momentum diffusivity thermal diffusivity. Mu is nothing but viscosity of the fluid divided by density, and alpha is nothing but K by thermoconductivity of the fluid divided by density of the fluid times specific heat of the fluid. So if we plug in these values in this, we will get mu Cp by K of fluid.